Hello and welcome to another computational geometry video. This one we're going to take it a little slow and we're going to talk about four problems. The key point between these problems that there's two pairs of them. One is in what we call one visibility, one is in two visibility. And the idea is that one of the problems is a covering problem, and the other problem is a I guess it's also it's a packing problem. And the packing problem is going to be a lower bound on the covering problem, and the covering problem is going to be an upper bound on the packing problem. And for a lot of shapes, these values converge. And the idea is that we will, through exploring some random examples. I have no script. I have no plan for exactly what shapes I'm going to do, but the idea is just showing a method that we often use in computational geometry. Now the first one, I'm going to go with the hidden set and convex cover problem. And those problems are a little less what we might call famous than the other two problems, the independent witness problem and the art gallery problem. But it'll make sense why I bring this up. So first I'm going to just mouse in a random polygon, like so. The first thing we know is that the hidden set, I went over that in detail in my last video. That hidden set number is less than the convex cover number, and we're going to use HS of P to refer to the hidden set number of P, and CC of P to refer to the convex cover number of P. Where hidden set is the number of points where no two see each other, and convex cover is the hidden set is maximum number of those hidden points, and then convex cover is the minimum number of convex pieces you need to cover this polygon. This will make sense in a moment when I start going through them. So let's do the hidden set in blue. So, okay, we can place a point here. And if we place the point here, this only constricts us to not placing any more in this little triangle here. So we're starting off good. We only have a small area that we're restricted to. Now I can use this nice little tool, and this is IPE, by the way, the program I'm using. And I can slide along the boundary of this polygon using the boundary snap. And my idea here is that if I do this, then I'm going to constrain myself yet again to another convex piece. So I'm going to do the convex pieces. I'll do them literally in green, and I'll do it as 10%. And the idea is if I keep this in blue, then I have to select the polygon tool. Then while actually I should put a dotted border, we can keep track of the convex pieces we've used. Okay, so this is one convex piece, and I'll make it dashed, sorry, not dotted. And the idea is that if we keep track of the number of convex pieces, and we keep track of the number of let's just put this up here because I know my next move already. It's a little like a chess game almost, trying to make sure you get the right number of moves. And okay, so we have two pieces, right? And they're both within convex pieces. We have 2 points and 2 pieces. And so far, this point, okay, it can see a little bit more than I've let on, but no worries. Now we have to choose our next point. And this one we will have to do rather carefully, because we want to make that point see as few other points as possible. So I'm actually going to scout out a point arbitrarily close to this vertex down here, and then another point arbitrarily along here. And it'll make sense in a moment why. So I'm going to just extend this out just so that I can get a little handle of my visibility regions that I'm going to be constructing. I should, what the heck? Okay, so yeah, we're going to pull this point over here. And, okay, so this is going to wind up being a convex piece corresponding to the point that is contained by it. And we'll take a line down here, and we'll get rid of this. That line was just for the purposes of just kind of getting a handle on the situation. But it should not be an issue anymore. So what we will do is we will take this almost parallelogram. It's really a trapezoid, but it looks almost like a parallelogram. These are just not quite pacing each other right. But okay, so now we have some pieces, and this point is in this piece, this point is in this piece. And also I should mention that convex cover, these pieces can overlap, but there's really no reason to make them overlap. Like, okay, we can get rid of this one and descend it down like that for maybe something a little simpler. But it doesn't really matter too much. Now the next point we want to do is, I'm going to say it should be around there. And the idea behind this is we want something inside of a new convex piece, and I'm going to get rid of the border snap for a bit. This is getting a little bit annoying. But that piece right there. So this point, I put it down here for a reason. I didn't want it to be able to see this, so when this looks at this corner, rather than being right across, that line that it is like that weak visibility line. So under certain ideas, it's not strictly visible under all definitions, but I use the more open definition in terms of visibility for certain reasons, but main one being that this right here, now we've also come into an issue. We're going to try and put a point in here, but we're not going to be able to cover this little region down here. So I was a little bit hasty here in trying to get that to work. But really, what I need is to, I'm just thinking, potentially I may drag, this might not be this might not be an ideal polygon, but we'll figure our way around this. So really what we want to have is take this. You see, this is like, this little triangle here is becoming a bit of an issue. And there doesn't seem to be a whole host of ways around this issue. Actually, there's one way. There's one way. Yes, I figured it out. Sorry. Okay, so we will be moving this point potentially. Well, the crux of this issue that we're coming into right now is that this triangle appears, and this may relate to its imperfection, but and I'm using the term perfect. I mean in terms of graphs. There's another idea of a perfect polygon, which is half related to the idea of perfection in graphs, and we'll go over in a little bit. But when we go to the next pair of problems. But okay, let's continue on anyways. Where were we? We put this guy over here. And so the choice really is cover this little white area or potentially miss this lower area here. Because this line comes in like this, is going to be the crux of the problem. So it's a little difficult, but we will trudge on. We will go with covering that small triangle for the moment, because we may be able to come up with some a more difficult proof, but definitely not the way I was planning on going for this nice little relaxing session. So we are going to take this out because we want to get this convex piece as much as possible. And I suppose we can go like that to get it. And we will just make that one little line there to finish that picture. And this last point, this last hidden point, we'll throw in there. So the idea is right now we have that the hidden set number, and this may happen a lot, hidden set of P is greater than or equal to 1, 2, 3, 4, 5, 6. Oh, sorry. Yes, greater than or equal to 6. And that's the annoying thing about IPE is that whenever you change the opacity, we come into issues. And then CC of P, we know that the minimum convex cover must be less than the one we found here, because we found a convex. Well, including this point right here, this triangle, we have a convex cover of size 7. We can probably do better than that. Or we provably can't. It is really one of those two options. Okay. The quickest way of going about this, this is a more advanced technique. Let us place a point. I'm going to go with a more refined outlook. So this point is not a hidden point. However, the idea is if we can, so we're going to have to add in some more points in here. So we'll add a point here and here, and I'll explain why we need these points where I'm putting them. And the idea is we want to create a subgraph. And this is something that I'm going to mention in my Young Researchers Forum talk. But the idea is when we're doing hidden set and convex cover, we need to use subgraphs when we don't have our numbers adding up nicely. So what we will do is take this subgraph, and honestly we can even constrict this to be a lot less complicated, but we may want another point, that point being The idea is we want to represent what this either this triangle or the triangle that was in here has to be not represented. So I'm going to redraw that line and try and reform that triangle. That was not the line. It's this line. And yeah, so when we use this point, when we use this edge and kind of ride along it, we necessarily can't cover a little bit of that area because this line comes like that. So it gets a little tiny triangle in here. So let's just place even smaller. Even smaller doesn't work quite right. So we're going to have to make an X and turn on, we have intersection. So we're going to go with that small little X. Get rid of that. So that small little X is within that triangle of doom that we had earlier. And the idea is we want to show that a click with the points, a click cover is not possible. I have made a grave mistake. Okay, yes, I have way overcomplicated this issue. And apologies to those watching this who have realized that I can probably fix this by simply doing that and turn down the opacity greatly. Great, okay, that is a lot less complicated. But that's how a lot of this these problems work. Oh no, now greater. That sometimes you just need to do a little bit of thinking and you will get right where you need to do. So, perfect. No need for the graph theory. But we were going to get into it. Maybe I'll show an example in a bit of where that gets more complicated. But basically, the idea is, for hidden set and convex cover, for these homestead polygons, as I call them, they are very easy to find in terms of a homework problem. Having just a student practice this is not terribly demanding. For some shapes like this, I get a little bit caught up with trying to make sure there's not too much overlapping, but because it becomes a little less clear. So like using the 10% often makes it a little easier because you see, okay, that's double covered, but generally I don't like to do too much double covering. Ultimately, we have we have this. They're both. So the hidden set has to be larger than the observed hidden set. The maximum one has to be larger than or equal to the observed hidden set, and the minimum click cover has to be less than or equal to the observed click cover. And since they're equal, we know that that collapses, and that's what we call a homestead polygon. So yeah, that's how you find hidden set and convex cover just by pen and paper. I'm going to pull these up. I'm also going to make this back to 16 point because first 16 point, and then if I draw it in 16 point, then I can kind of whittle it down. All right, let's try and find. Okay. Now I'm going to take this same shape and I'm going to do the other problem, which is, so the first problem was in what is called visibility. One visibility means that if 2 points have min-link distance 1 or can see each other in the most obvious way, then they are mutually visible. In 2 visibility, you have 2 points can see each other if they're within min-link 2 of each other. So this one, if we go to a point here, that point sees both of them in common. So this problem is actually usually defined in terms of one visibility, but reason I bring up the two visibility idea is because it's hidden set. It's the same idea. It's also an independent set. Or on the contrary, the other problem is a convex cover in two visibility. So the first one is called the witness number, and that was an idea. Independent witness set was an idea first developed by Professor Joseph Mitchell out at Stony Brook University, where I currently study. And the other idea is the guarding problem, which has existed for a while. It was first invented by Klee, I believe, Victor Klee, I believe. I'll update in the description whether I got his first name correct, but it's a very old problem. But a lot of the early work was done by Kvaddel, the man who presented the first proof of the combinatorial upper bound of the floor of n over 3 of that theorem, using a comb-like structure with an induction. I have not looked through the proof terribly. I should say it's the guarding problem, the arc gallery problem. I haven't looked through it very thoroughly, but it's a very interesting idea. It was made much more easily by Fisk, so that's the main reason. But anyways, the independent witness problem is a lower bound for the guarding problem, not garden. And the idea behind these is that the guarding problem is instead of trying to get a covering in terms of making all these shapes convex, they don't have any reflex vertices. All we care about is that whether they can all be seen by a common point, and those common points are often called guards. Now, usually the way that we do witness points is by we'll do the witness points first. We won't be trying to do one and one. And the idea with the witness points is that instead of being hidden in one visibility, they're hidden in two visibility. And there's important graph theory ideas behind why that's the case, in terms of what that means. So in this graph, right, if you drew the point visibility graph, well, that's nothing for these guys. But the idea is that if you went into two visibility, well, then these guys are within two of each other. And actually, these guys are within two of each other. And these guys are within two of each other. You can't stretch it so that those are. These two are within two of each other. These are within two of each other. These are also within two of each other. And then these are within two of each other. So it's a connected graph in terms of the two visibility. But and that actually, I don't know if that's proven, but I think an easy proof of that would exist. That a hidden set in terms of the power of the greater graph, actually that should exist. It's connected. In fact, that actually, yes, that must make sense. Anyways, sorry, that was a little aside on my own thinking. These would not be an independent witness set. You'd have to grab an independent set of points from this graph, which might include this point, and then maybe this point. Actually, this point wouldn't be independent because, once again, these are connected. So maybe more along the lines of, and even these ones are. See, this graph gets really complicated. So let's I always mean to do the select and then I press A. Okay, so let's start off with the witness points. Let's start with this point. It's often a very good idea to get corners. And the idea is that this witness point sees this area. And in fact, no, I will not do that yet. So it sees all this block, and I will use violet to represent this area. And no, I do not want the opacity all the way up there. I like opacity 10, sometimes for the lighter shapes like, the lighter colors like violet, it doesn't come out that well, but we will see. So any point in this area really will stretch into this witness area. So let's just move on to the stuff we will know. So this area is a nice little corner. We can build our next little witness sort of cell. If we keep the witness cell somewhat convex, then typically there is less issues involved. And now here is where we start to make observations about how many more we can really fit in. We can probably fit at most one more point. And that point I'm going to just put there. Actually, you know what? I will put it along here for simplicity, just because it's easier to draw this. We'll go up, we'll go down, and we'll go across. And then we go a nice little tour around. And yeah, this is a rather large area to be witnessing. But we will show, so let's just do our witness point number. That must be greater than or equal to, because we could try to pack more, but let's see, it's greater than or equal to 3. And that has to be opaque. But now what we're going to do is do guarding. So the guarding number is we're trying to cover the whole thing, or take points instead of convex pieces that are, so all the points in a convex piece have min length 1 from each other. All the points in a star-shaped polygon are at most 2 away from each other. So the idea is that it's like an analog. We'll do our stuff in green again because we're doing a cover. And we could start by just taking this point, right? This point is going to be able to see this side of things and this side of things. I mean, we could go as far out as one of these, but I don't think we're going to actually get anything that we really want out of that. So let's just go like that and then build the area that this guard sees. And honestly, we can get rid of this idea of the guard. It's really not doing much for us because this is a star-shaped polygon. So we're really covering with these star-shaped polygons, but it's nice to keep an idea of the centers of those so that we can keep track for ourselves. Why is this star-shaped? And these, unlike the independent witness points, these can actually cross over each other. We're just trying to figure out a way of covering the whole thing. So now we have to make a choice. We have to cover this area. Could we have... No, that's the reason. Okay. So if we want to cover this area, we have to be to the right of this line. If we want to cover in here, we have to be to the right of, well, I mean, that gets a little relative. We might see more as a left of this line. So it has to be, let's put a point right at that intersection so that we know that we can see up into here and up into here. And let's just extend this line like that, and that actually makes sense. Um, but yeah, so we're gonna build our visibility range. Really, it goes all the way up into here, but for ease of use, let's just cut it off there. For ease of the drawing, so that sees into there, and because of our selection, it sees all the way into there. Perfection. Now, it's as simple as just picking this point right here, and we will know that the rest of this can be seen from that point. And that confirms what we had believed, that the guarding number will now be, guarding and witness number are both going to be 3. So let me just write out that that is the G of P. And there we go. So these are the two problems. They both happen to be a homestead polygon, which means that the hidden set number and the convex cover are equal. And it happened to be a perfect polygon, or a polygon where the witness number and the guarding number are equal to each other. Now let's, for the sake of being extensive, let's draw two polygons where they are. I suppose I probably did not have to delete those. I could go to a new page. Let's make a polygon that has hidden set not equal to, this is going to be a little bit difficult, hidden set not equal to convex cover. So me and my co-author Eric came up with, independently, we both at different points in our progress came up with this shape, and we call it a wide star. And let's just make 2 of these. We gotta rotate them, but we have to rotate it around the exact center. So we gotta do a Control F1, and we gotta just rotate this around. Like that should be good enough. And yeah, so what we do is we go and we make these just deviate enough. In fact, I don't feel super great about how that's looking. But the idea is we want to get these they are not crossing in the ways that I usually like to make these. But it shouldn't be too much of an issue. The idea is no. Let's actually just try this. It has been a good while since I've made one of these wide stars, so let's just try like this. No, this will not work. I do not know why I am having a lot of issues with this idea, but we need to get rid of that one. I remember now, sorry. Sorry for the delay. Okay, so we will grab these goodies of a regular 5-gon. It has to be an odd number. Or at least we believe it has to be an odd number. Nope, we don't want to translate it, we want to rotate it. Yes, so. And that is actually not sufficient. We want to have a 10-gon. A regular 10-gon. So a regular 10-gon. And the idea is if we bring this into, nope, not translate again, then these should go like we want. And of course, of course. I just happened to pick the circle. That would be an issue. The main idea here, and I am probably quickly losing the point of the point here, but we want to make something where the hidden set number will be just 2, but the convex cover number will be strictly 3. And those convex pieces are kind of being constructed right now. Hopefully this, well, this also may strike down another idea. This will strike down the idea. Oh no, it won't. Anyways, so let's get rid of these guys in the middle because they're being annoying. So this should be a wide star, and that is a polygon for which we go never mind. Okay, so actually, this is a bit more finicky than I remember. I guess this is better left as proof. So okay, when you try things like this, it sometimes it doesn't work out. I'm glad that it worked out this way, getting the hard one to not work, rather than the just the example to get you going into the problem. But the wide stars are a class of polygon that me and my friend Eric have been investigating, where the hidden set number and the convex cover number are distinct, and that is something that is a bit rare. It doesn't seem to really pop up a lot. For a while, we thought that all polygons were what we call homestead polygons, and that was a failed conjecture. Eric found the example, I proved it, and it was interesting looking at how an idea that we held on for months kind of fell apart in a matter of days. But it was a real good learning experience for us. Learning a little more about the field and how discrete and computational geometry is not exactly always as it seems. It's not always the easy answers that are at least not the interesting ones. So this line will necessarily be enough to make that convex. So what we need to do is go back to the point, which is that the circle on the outside needs to be bigger. It's been a while since we've really been working on the homesteads. So I am rusty. But this may be more like a wide star. yeah, so I really love this field. I love discrete geometry especially. But making the algorithms is important. Proving hardness of algorithms, proving hardness of problems, hence disproving the idea that there's really any fast algorithms. It's important work, and sometimes I find myself getting very entrenched in the math of it and accidentally creating convex shapes when I want concave shapes. So yeah, I will look back at the wide stars, and maybe in another video I will present them. But let's just go with the. Now I don't even remember how to do Godfrey Toussaint's favorite polygon, but so I guess this has been a nice little discussion of polygons. And the two problems in graphs, independent set and convex cover, and showing how they have two analogs within polygonal spaces, namely hidden set and convex cover. Hopefully this more laid back video is something that you guys like. If not, then it will never happen again. But yeah, so I'm going to try and do more of these laid-back problem-solving videos where I kind of go down some routes, try and remember some ideas, and if I don't, then it's not the end of the world. I just want to try and help not just talk about the theory, not just talk about the programs, the coding, although I should get more into some of the... Maybe I'll do a live coding sometime, but... basically, I was going to do this as live. This was going to be a live video, but I ultimately was not able to do that because YouTube has a problem with trying to set up a live without asking beforehand. So next time I should be able to do it live. But I had a nice week, so I figured towards the end of it, might as well try and finish off with some nice little problems. Yeah, so that's the hidden set, convex cover, the independent witness set, and guarding problems summed up. And here's a really good example and a really good demonstration of the problem-solving process and how it's not always linear. You know, sometimes you find little empty triangles and then you realize that really if you just went one step further instead of just trying to constantly think 2 steps ahead, sometimes it's better to just do out an iteration, and you'll find that maybe you're not in such a pickle after all. So I hope everyone had a good time, and if not, let me know in the comments what I need to do better. And hopefully this channel will get a little bigger, and hopefully we can expand the horizons of computational geometry and expand how many people, its audience, how many people know about it. Anyways, have a great day, and hope you enjoyed this.